now that we know how to fit different kinds of distributions to a particular data by using fit distribution plus package, and within that using the function like fitdist. So we have looked at how we can use the fit distribution package, fit distribution plus package, and within that using the fitdist function to fit some kind of distribution to a data. So we have tried fitting a gamma distribution to a particular data, or I may think of fitting a normal distribution to a particular data, right? So now that we know how to fit a distribution to a given data, and based on that get an estimate of the parameters of that distribution. If I am fitting a normal distribution, I can get mu and sigma. If I am fitting a gamma distribution, I can get a shape parameter and a rate parameter. So the most appropriate distribution with each of these parameters is typically provided by this fitdist function. Now we also have checked out what is the way I can compare between the distributions also. So some of the methods which we have looked at is log likelihood. So whichever is the method that is giving me a very high value for the log likelihood, that would be the most preferred kind of distribution. Similarly, we have looked at Akaike information criteria, which is like a measure of error, or even Bayesian information criteria, which is also a slightly different form of error. So wherein we want this particular error to be as less as possible if I have to choose a particular model. So these are some of the methods that we have already discussed when we are fitting the data to a particular distribution, right? So what I really want to look at here is, in some cases I can fit the data to a very general kind of a distribution, very normal one like a gamma or a Pareto or Weibull, something which is already known. Or in some cases I can even think of fitting a mixture distribution. Means there is some probability that it is let's say a gamma distribution, and there is some other probability that it is a Pareto distribution. So we can even fit those kind of models to the data. So whatever is the model that we are fitting, we have to really assess which model is an appropriate fit to our data. So apart from these mechanisms of log likelihood, AIC and BIC, here in this session we are going to look at various other methods through which we can measure which model is more and more adequate to this particular data set. What is the adequacy of the model that we have chosen for this particular data set? So there are different kinds of mechanisms that we have, right? So we can try out different kinds of mechanisms, different ways in which we have fitted the data, and then try out which one is more and more adequate for our data. So let's go ahead with it. Some of the mechanisms that are readily available for us to do the process. The first one is a histogram of the models that we have fitted, right? We have a histogram along with the empirical densities. So I can get the histogram plotted along with the empirical densities for the same. So empirical density is more coming from your actual data, histogram is coming from the fitted model. So fitted versus the actuals, we are trying to look at that. Similarly, the other option is, instead of looking at the densities, we can look at the distribution function plots, So we can look at the distribution function of the actual versus the fitted and see what is the level of fitment or the deviation. Then we can also look at the QQ plot and the PP plot, which are again other ways of really coming out with whether my data is more and more appropriately fitting to a particular distribution or not. And then we have real statistical tests which assess the goodness of fit. Right, earlier we have even looked at the CVM mechanism. Right, these are the various assessments of the goodness of fit. Apart from Akaike information criteria as well as the Bayesian information criteria. So we will have a quick discussion about them. And finally, we also have the Skewness-Kurtosis graph, which simply which represents what is the level of adequacy of a particular model to a particular data set. So all these things we will try out with the one single example that we have used earlier, right? So let's go ahead. First thing is histogram. We know how to plot a histogram. The observed data are divided into k classes, k different groups. Generally we would prefer k to be more and more in line with the proportional to log n. So depending on what is the size of my data, I would prefer those many classes to be there as a part of my data. Again, though it's not a hard and fast rule, this is just a kind of a ballpark kind of a picture. So the number of observations in each class I am computing, which is what we are calling as a frequencies, and accordingly the rectangles are drawn. So we have a direct formula called hist, which is taking care of plotting of the histogram for any data set. So we are going with an estimator of empirical density. When we are talking of histogram, it's a kind of an estimator of empirical density, wherein the area of each rectangle is typically proportionate to the probability of occurrence of that particular area in that interval. So first thing, we will first plot, we will first fit a model. Right, let's try out 2-3 models on our data, which we have earlier done. So I am taking this cost variable itself, cost data set that we have used earlier for fitting the models. Just as a quick revision to what this actually contained, I am doing a simple head. So it contains X, date and ultimate cost. I am only taking the ultimate cost here for our workout purpose. Right, so let me take this a small variable x, a small letter x, which I am taking as cost dollar ultimate cost. So I am taking only this ultimate cost column from here, and all other things I am ignoring. So this is the one that I have. Based on this ultimate cost, we will fit different kinds of distributions. So we'll try out 3 different distributions, right? All of them will go with maximum likelihood approach itself. So let's first fit a normal distribution. Normal distribution, I am calling it as NOR. So this NOR for me, first let me take this X as let me simplify it. Instead of having that big a numbers out here, let me reduce them in terms of million. So let me divide it by 1 million. Okay, so if I look at the summary of X, so these are small numbers to work with, fair enough. So now let me fit a normal distribution to this data, right? So I'm calling it as, I need to load this library fit distribution plus. If it is not there, please install it, because we already have it. I'm simply loading it. Fit distribution plus is the package that we have loaded. Now within that, let me call normal as a variable, which is using the fitDist function. Just to recollect, fitDist function actually uses the name of the variable, which is x, the name of the data, which is x,